So the Unit 5 review sheet. Number one, two stores sell watermelons. Um, First store, right? I'm going to just make a chart for this. Store A, you got an average of 2, standard deviation of 2.5. And at store B, average is 1.8, standard deviation of 2. So I'll just make myself a quick chart. And then so for question A, that's what's the mean and standard deviation for the difference in melons. So in other words, A minus B. And so the mean or the expected value of A minus B, you'll just do 2 minus 1.8, which is 0.2 pounds. And then the standard deviation of A minus B. Remember, we want to first convert to variances, 2.5 squared and 2 squared. And you always want to add those variances. And so once you do that, that calculation is going to be 3.2 pounds. Part B, if a normal model can be used, what's the probability that the melon you got at the first store is heavier? So in other words, the probability that A is greater than B. Remember the trick that we're going to play? So that we get a critical value, we're going to subtract B. So we got probability of A minus B is greater than 0. At which point we need to go and get a z-score. So our critical value is 0. My mean, which we just saw in part A, is 0.2. And my standard deviation, which we just did in part A, is 3.2. And so that z-score is about negative 0.06. Right? So we're not very far below the mean. But just as a quick reminder, as we set this thing up, right, this should be centered at 0.2, and 0 is just a little bit below the mean, and we wanted to shade up. So it's more than likely that we get a heavier watermelon at the first one. So if you did your normal CDF, lower bound is 0, upper bound is infinity, we're centered at 0.2, the standard deviation of 3.2, we should get a probability that it's about 0.52. So there's a 52% chance that we get that heavier watermelon at the second store. And then finally for part C, the first store sells them at 32 cents a pound, the second store only 25 cents a pound. So find the mean and standard deviation, the difference in price. So what we're going to have to do is make a quick conversion. So in other words, we need to multiply everything in the first store by 0.32 and everything in the second store by 0.25. So if we take a quick second, 0.32 times the 2 pounds, so the mean now is 0.64, and then 0.32 times the original standard deviation is 0.8, and then in the second store we're going to multiply everything by 0.25, end up with 0.45, 0.5. So our new expected value for 0.32A minus 0.25B equals 0.64 minus 0.45, which is 19 cents. And then standard deviation of 0.32A minus 0.25B, right, because we're converting. Remember, we still want to go ahead, convert them both. The variance, add them, take the square root of that. That's going to be about 94 cents. There's a lot of variation in the prices. All right, let's move on to number 2. You play 2 games against the same opponent. The probability you win the first game is 0.4. If you win, the probability changes all of a sudden, which all of a sudden means right here, these are not independent because probabilities aren't staying the same. That's one of our issues for a binomial situation. So we're actually not in a binomial situation for part A. So if we lose the first game, the probability you win the second is 0.3. So are the 2 games independent? No, probabilities are changing. B, what's the probability you lose and you lose? So the probability you lose the first game would be 0.6, right? That's 1 minus 0.4. Goes up here. And then if you lose the first game, the probability you win the second is 0.3, which means the probability that you lose again is 0.7. So it's 42% chance that you lose both games. What's the probability you win both games? So win and win. So the probability you win the first time is 0.4. And it says if you win the first game, the probability you win the second is 0.2. We actually don't need this 0.3 right now because that's in the case that we lost and then we won. So here, 0.08. Part D, let x be the number of games you win. And so x can take on the values. You could win 0 times, 1 time, or 2 times in this scenario. So for us, 0, 1, 2. Probability we won 0 games, but we actually already have that. That's 0.42. The probability we win 2 games, well, that's 0.08. And then really we could go through and try to figure out all the different scenarios for 1 win, or we just use our probability must sum to 1, so just go ahead and fill in that missing chunk. And then for part E, what are the expected value and the standard deviation? Put that chart into list 1 and list 2, and you'll get an expected value of 0.66 wins and a standard deviation of about 0.201 wins. All right, on to number 3. So an Olympic archer hits the bullseye 80% of the time, so we have a probability of a hit equals 0.8. Assuming each shot is independent, that's part of our binomial. Shoots 6 arrows, n equals 6. There's 2 outcomes, hit or miss. So we're looking at a binomial situation in number 3. First bullseye comes on the 3rd arrow. That's geometric. She misses the bullseye at least once, so this is just binomial. First bullseye comes on the 5th arrow. This is geometric. And these are all binomial. So this is going to be good practice with our PDF and CDF information. So for part A, first bullseye comes on the 3rd arrow, so the probability that x equals 3. So that's geometric. PDF, it's a particular value, and so it's 0.8, comma 3, and that value, if you plug it into the calculator, should be 0.032. For part B, she misses the bullseye at least once. So in other words, if x is the number of hits, that means that she gets less than or equal to 5 bullseyes. So here we're looking at, we don't have to do anything tricky, so that's just binomial CDF. 6 shots, 80% chance, less than or equal to 5, and that's going to be equal to 0.74. For part C, our first bullseye comes on the 4th or 5th arrow, so probability x equals 4 or x equals 5. So this one's a little bit tricky. You're going to have to do geo PDF 0.84 plus the geometric particular value at 5 as well. So you have to actually do that twice. A lot of work involved. But 0.0077. She's a pretty good shooter, so it's not very likely it takes her that long to hit the bullseye. She gets exactly 4 bullseye. So here we're just taking the 6 shots. It's not until success, so this is a binomial PDF. So out of the 6 shots with an 80% probability that we're at 4, and that's going to be 0.246. Please slide down. E, she gets at least 4 bullseyes. So probability x is greater than or equal to 4. Here's where we got to remember to play our trick. We need 1 minus the probability. The opposite of greater than or equal to 4 is actually less than or equal to 3. So 1 minus binomial CDF 6.83, and that's equal to 0.017. And probably she gets at most, so that's probability that x is less than or equal to 4. No tricks here. It's just binomial CDF 6, comma 0.8, comma 4, and that's 0.998. On to number 4. In the 4x1 relay, we have these swimmers that are independent. Excuse me. If I can get that to stay out. We've got a normal model, and the mean and standard deviation are shown below. So what are the mean and standard deviation for the team's total time in the event? So what we're going to do then is add all of these together. And then to get standard deviation, remember, this is a great place to go do it. Go ahead and move everything over to variance. So this is 0.0576, 0.22 squared, 0.0484, 0.25 squared, 0.0625, 0.21 squared, 0.0441. So the mean and the standard deviation, the mean, you're just going to add all those together. So 1 plus 2 plus 3 plus 4. And then for standard deviation, remember we want to go ahead, we've already done the squaring. add all the variances, 1.0441, and you need to come back and take the square root. So the value for the expected value and the standard deviation would be 200, basically 200.5 seconds with a standard deviation of 0.46 seconds. So the team's best time so far is 3:19.48, which is 199.48 seconds. Do we think they're likely to swim faster than that at their conference championship? So since we're in a normal model, we're really looking for what's the probability if we let x equal the team's time. I guess really we should say the team's total time. And so what we're looking for, what's the probability x is under 199.48, sorry, z-score, 199.48 minus 200.57 divided by my standard deviation of 0.46. So our z-score for this particular problem, z-score there is negative 2.37, which right away tells us it's not very likely it's going to happen. But if we take a quick look at a normal curve, which should be centered at 200.57, so we're pretty far below or over 2 standard deviations away. Not very likely. Let's go ahead and find the area. All right, so the normal CDF from negative infinity up to 199.48 with a mean of 200.57, standard deviation of 0.46. So the actual likelihood of that happening 0.009. So basically just under 1% chance that they actually swim better than their season best at this point in time.